You dictate a text message. You ask a smart speaker for the weather. You get an auto-transcript on a YouTube video. All three are the same task. Air pressure moving through space at 44,100 samples a second turned into typed words, which is astonishing. Sound has no letters, no spaces, no grammar, just a wobbling scalar. And somewhere in the middle of the pipeline, the wobble becomes ESET, an alarm for 7. This video, how automatic speech recognition works. From the classical pipeline that ruled from 1970 through 2010 to the deep learning acoustic models that took over in 2012, to the end-to-end neural systems, to wav2vec, to Whisper, which does near-human transcription in 99 languages from a $15 Raspberry Pi. Last video ended with natural language generation. Text out. Now we're going the opposite direction. Sound in, text out. This is speech recognition, the other half of the audio pipeline. And it has been an active research field for longer than natural language processing itself has existed as a name. Bell Labs was building digit recognizers in the 1950s. Today's puzzle. Speech recognition was viciously hard for 50 years. Every era took a factor of 2 error rate cut and called it a win. Then in 2020, self-supervised pre-training and a very large diverse audio corpus made the problem look almost solved. What changed? And is it actually solved? Today's 3 beats. First, the classical pipeline. Raw wave to MFCC, features to HMM-GMM acoustic model to language model, to a Viterbi decoder, the shape that dominated for 40 years. Second, the deep learning takeover. Hinton 2012 replaces the GMM with a DNN, then CTC loss, then listen to 10 spell, one network, wave to text. Third, the self-supervised era, wav2vec 2.0, Whisper, 680,000 hours of noisy web audio, multilingual, robust, near-human on clean speech. Beat 1. The classical pipeline. Start with the raw wave, a scalar sampled 16,000 or 44,100 times a second. That's too much data and none of it is directly useful. Chop the audio into overlapping 25 millisecond windows, 100 windows per second. For each window, compute a spectrum. How much energy is at each frequency? Then compress that spectrum into about 40 numbers using the MEL scale, a perceptual frequency scale that matches human hearing. Those 40 numbers per 10 milliseconds are MFCC features. That's the input to everything downstream. Now the acoustic model. Given the MFCC features of one 10 millisecond frame, what phoneme is being spoken? The classical answer, an HMM with Gaussian mixtures. Each phoneme has a Gaussian mixture model over MFCC features. Rabiner's 1989 tutorial paper on HMMs made the field. The HMM state transitions modeled the fact that phonemes take multiple frames to say "aish" sound lasts many milliseconds. HMM-GMM was state-of-the-art for 20 years. Then the language model. Prior over word sequences. The cat-sat is common, cat-the-sat is not. N-gram language models on billions of words. Combine the acoustic prob with the language prob using Viterbi decoding, a dynamic programming algorithm that walks through all possible phoneme word paths and picks the one with the highest joint probability. That is classical ASR5 components, each one hand-tuned, ran on a laptop in the 2000s. Beat 2, 2012, Hinton and colleagues. Replace the GMM in the acoustic model with a deep neural network. Same HMM state transitions, same MFCC input, same Viterbi decoder, just a DNN instead of a Gaussian mixture predicting phoneme probabilities per frame. Cut word error rates by roughly 30% overnight. Every major ASR lab converted within 2 years. Then the field pushed the neural network further. Why keep the HMM at all? Why keep MFCC features at all? Graves 2006 introduced CTC, Connectionist Temporal Classification, a loss function that lets a neural network output text directly from audio without an explicit alignment. Then Chan and colleagues at Google 2016. Listen to 10 spell. Encoder-decoder with attention, wave in, characters out. One network. No HMM, no language model, no Viterbi. It just reads. The trade-off. End-to-end neural ASR needs a lot of labeled data. hundreds of thousands of hours of transcribed speech per language. Rich languages get great systems. Everyone else, nothing. That gap was the next problem to solve, and the fix arrived in a strange place. Copy an idea from Bert. Beat 3. wav2vec 2.0, 2020. Viterbi and colleagues at Facebook AI pre-train a transformer on raw audio using a contrastive objective. Mask spans of audio predict which of several candidate representations is the real one at each masked position. No labels needed, no transcripts, just hours of raw speech, then fine-tune on tiny amounts of labeled data. 10 hours of transcribed audio in your target language. That was enough to get near state-of-the-art recognition. Then Whisper, OpenAI, 2022. Different approach. Skip self-supervised. Just collect an enormous amount of noisy labeled audio from the web. 680,000 hours. Multilingual. Songs, podcasts, lecture recordings, bad audio, good audio, all of it. Train a transformer encoder-decoder to transcribe it. And it works. Robust to accents, noise, background music, code switching. 99 languages, one model. Where things stand in 2026. Clean speech in a major language. Solved. Approximately at human word error rate. Noisy speech, heavy accents, low resource languages. Still hard, but wav2vec style pre-training, plus small labeled corpora work. Spontaneous overlapping conversation between multiple people, still open. And ASR is now fast enough to run in real time on a phone. What was a lab-grade demo in 2010 is a Raspberry Pi in 2026. 3 takeaways before the quiz. 1. Classical ASR is a 5-stage pipeline. Wave to MFCC, to HMM-GMM, to N-gram language model, to Viterbi decoder. Rabiner's 1989 HMM tutorial made the field. Ruled for 40 years. 2. Deep learning arrived twice. Hinton 2012 swapped the GMM for a DNN in the acoustic model. Then CTC and listen attend spell went end-to-end. Wave in, characters out, one network. 3. Self-supervised era. wav2vec 2.0 pre-trains on raw audio with contrastive prediction. Whisper collects 680,000 hours of noisy web audio and trains through it. Multilingual, robust, near-human on clean speech. Quiz 1. What are MFCC features in classical ASR? A. A machine learning classifier used only for language ID. B. A 40-dimensional per-frame representation of the speech spectrum on a MEL. Perceptual, scale computed roughly 100 times a second. C. A specific type of neural network layer. Or D. The output of the language model. B. MEL frequency cepstral coefficients. The classical audio feature. Chop into overlapping 25 EMS windows, compute a spectrum, warp it onto the MEL scale, take a discrete cosine transform, keep the top 40 numbers. That is the input to every classical acoustic model, and still the input to a lot of neural ones. Quiz 2. What did the 2012 Hinton et al. Paper change in the classical ASR pipeline? A. They replaced the entire pipeline with one giant transformer. B. They replaced the Gaussian mixture model inside the HMM acoustic model with a deep neural network. Everything else stayed the same. WER dropped 30% overnight. C. They eliminated the language model. Or D. They introduced MFCC features for the first time. B. This was the first place Deep Learning 8 ASR. Just the acoustic model. First, HMM stayed, Viterbi stayed, language model stayed, only the frame classifier changed. That was enough to flip every major lab in 2 years. Quiz 3. How does wav2vec 2.0 allow good ASR in low-resource languages? A. It requires hundreds of thousands of hours of labeled transcripts per language. B. It pre-trains on raw, unlabeled audio with a contrastive mask prediction objective, then fine-tunes on very small labeled datasets. Tens of hours can be enough. C. It hand-labels new languages with volunteers. Or D. It translates every language to English first. B. Same idea as BERT for text, ported to audio. Mask spans of audio, Learn to distinguish the correct latent representation from distractors, all from raw audio. Then fine-tune on a tiny labeled corpus. This is what made speech recognition viable for languages that never had ImageNet-sized transcript corpora. Back to the puzzle. What changed to make ASR go from viciously hard to near solved? Two things. One, end-to-end neural nets ate the classical pipeline stage by stage. Two, self-supervised pre-training plus enormous unlabeled audio corpora broke the data barrier for low-resource languages. Speech recognition is the closest NLP task to solved in 2026. Next video, the reverse direction, text-to-speech. Next time, text-to-speech. The other direction, words in, waveform out, concatenative snippets, parametric HMM synthesis, tachotron, WaveNet, and why the voice you hear reading this course sounds like a real person. Hit subscribe.